Welcome, everybody. Thanks for joining us. My name is Jolie McGraw, the Distribution Coordinator at ThermTest, and I'll be the host for today's webinar. Today we are presenting thermal conductivity of soil and concrete using transient line source technique, presented by Dr. Daniel Cederkrantz. I'd like to mention our upcoming webinars for August and September. All attendees will receive an invitation via email, and registration will be available through our website in the coming weeks. At the end of the webinar, questions will be answered by Dr. Cederkrantz with the remaining time. Please type your questions into the chat box at any time during the webinar. If we run out of time during the Q&A, remaining questions will be answered in the post-webinar email on Thursday, July 9th, along with the recording. Dr. Daniel Cederkrantz studied at Chalmers University of Technology in Sweden, receiving a PhD in material science with a focus on thermoelectric materials. He then became the Chief Science Officer at HotDisk until 2018, where he transitioned into a new role with ThermTest Europe AB. I will now pass along the webinar to Dr. Daniel Cederkrantz.
Thank you, Jolie, and hello, everyone. Nice to see all of you here. Even if you can't really speak with me, we can have a chat in the chat box later on here. But before we start, let's go through the agenda. And we have, first we will have a look at today's samples, soil and concrete, of course, which was the main topics here, of course. We will have a look at advantages of using our method of transient line source. We will also look at TLS 100, the machine itself. And we will look at who is the typical user of these devices. We will do a little bit of theory for you to get a little bit of more understanding of the machine. And we will not go too deep into it, but some things is important to know for anyone using a machine like this. We will also have a little discussion about the ASTM standard D5334, which governs the TLS instrument. And we will have an outlook to some other testing methods here. We will, of course, discuss how to use the TLS 100, see a little bit testing demonstration, and results that will follow. And as Jolie mentioned, at the end of it, there will be a little bit of a Q&A session. So don't be afraid to ask questions, and maybe if they're relevant, they might pop into the presentation even before the Q&A session, but I leave that up to Jolie, who will be moderating that. All right, so let's move on to the first real slide here. So why do we want to talk about soil and concrete here? Of course, these are two quite common samples to test with the TLS 100. Soil, first of all, that's our most common application for the TLS 100. You have it here. There are many applications where it becomes of interest. It can be because of underground cable installations, geothermal installations, and so on. And the properties of soil, everything from dense clay dirt up to very coarse sand, for instance, the properties vary very much, and the thermal properties will depend on your particle size, for instance, moisture content, and many other things, how the particles will stick together, for instance. Concrete is a quite different type of sample, but also a very common sample, of course, in any kind of structure, really. And thermal conductivity of concrete can, of course, be very important because sometimes you want the heat to propagate. Let's say you have floor heating. You want the heat to go through your concrete easily and not be wasted to the insulation layer underneath. But you might also want to have a low conducting concrete in your wall structures, for instance, to keep your building either warm at night or cool at daytime, for instance. So this is why we will look a little bit more into these two material types for this presentation. But let's go through a little bit more general information to start with. So something about advantages of using the transient line source as compared to other methods for testing thermal conductivity. First of all, this method is standardized is a standardized method for testing, especially then for testing in the field and of soil. So it's really the ideal method for testing soil, and it's very easy to use. You will need more or less no training, and anyone more or less can use it. Simply study your manual and you should be good to go. You will get your results very fast and easy. It takes a few minutes to run a measurement and you will get your results directly. You don't have to do any calculations in a software or anything like that. You get it on the screen even if you're in the field, and you can just note it down in your notebook or later on transfer it to Excel for further processing. It's also easy to use in this fashion that the machine comes factory calibrated. Each needle, I should say, is calibrated separately, which makes it also quite simple to, if you need to have more than one needle, you could quickly swap between probes. One way to use this is to speed up your testing, or you could have spare needles in the field, and if you run into trouble, maybe you damage a needle for some reason, you can just quickly swap over to a new needle and get going with your testing again. So it can really be a lifesaver, especially in the field, I have noticed, to have a spare needle and being able to quickly swap over to it. Another very important factor, I suppose, is that this machine is, compared to other methods, very affordable. Exact prices we can discuss privately with everyone because it might vary a bit on your markets, but in general, it's a very affordable instrument. And you will get everything in one case, but we will come a little bit back to that. And it's not big and bulky, so it's nice and easy to work with. So here's a little overview of the device itself, the TLS-100, as we call our TLS device. As you see here on the picture, you have the instrument, and we have the two needles, the long 100 millimeter needle, which is our standard needle. It's ideal for testing soil and loose samples, powders of any kind, basically. And we have a shorter 50 millimeter needle, which has a bigger diameter, making it perfect for testing hard samples, rock, concrete, asphalt, things like that, where you need to make or drill a hole, because trying to drill a hole which is 10 centimeters deep and 2 millimeter in diameter in concrete can be kind of a nightmare, but a 50 millimeter deep hole with 4 millimeter in diameter, quite doable, no big issues. Conductivity range, you see it up here, 0.1 to 5 watts per meter Kelvin, which more than well covers anything soil related. It will also cover concrete, more or less of any kind. So it has a fairly wide range of applications, from soil, polymers, rock, stone, concrete, glass, and so on. Thermal resistivity is also a result that you will get from it, and it is really the inverse of the thermal conductivity. A test time is something like 3 minutes. If you use the North Standard needle, we use a little bit longer test times for the 50 millimeter needles, then you have a 5-minute test time. Reproducibility, so if you put your sample in and you repeat the test several times, pretty good. About 2%, usually better. Accuracy, when compared to other methods, typically better than 5%. If you come to the very highest levels, maybe we will reach this a bit if you use the thin needle, but typically better than 5%. The temperature range allows you to use this machine really in any normal outdoor temperatures, of course. It also allows you to do testing inside, for instance, a climate chamber. If you need to test up to 100 degrees, the needles will handle that. And you can also test extremely low temperatures if you need to. So you could put it in a climate chamber or a freezer to come down to about minus 40 degrees. So it's a fairly versatile when it comes to temperature ranges. Of course, the machine itself will not generate these temperatures. That's up to you or a climate chamber. Sample sizes might be important to have a look at. First of all, largest sample, there is no limit really. If you're in the field, for instance, your sample will be the trench you're testing in, for instance. Then simply the needle will go into the trench wall or the trench floor. But if you bring samples to the lab, they should be placed in, for instance, steel tubes with at least a diameter of 50 millimeters and a length which is at least the same as the needle that you want to use. We need to make sure that the entire needle is covered by sample always. You cannot have half the needle covered only. So 50 millimeter in diameter, and a length which makes it possible to cover the entire needle. And we have the standards. We will come back to those very shortly. So let's move on to see what you actually get if you get one of these machines. So the machine comes, as you see here, in a suitcase style, easy to carry casing, which is very portable. It's waterproof even, so you can bring it with you in a rainy day and so on. You can keep your instrument protected inside. And it's really designed to be brought to the field and carried around and take a beating if happens. Maybe just throw it in the back of your car, it will survive. It holds all your accessories in addition to the instrument. You see here a verification sample, which we use to come back to and test that the needles that we bring are operational. You have thermal paste in here, which we use when testing solid samples to make sure we have good contact. You can keep your batteries if you need spares. Some other accessories like drill bits and a poker in a pouch here. And you can have 50mm needle can come in here, and you can fit at least 2 needles on this side for the long one. So all you need comes in one, easy to move around in bag. Okay, so that's the instrument. But who is actually using a device like this? So we do have users in all kinds of fields really, but typical users are researchers, engineers, and different kinds of technicians in the field. The applications where we see most use right now is, of course, as mentioned before, underground cables. Why is this important? Well, if you have a cable, you don't want to oversize it, for instance, and when you go down in diameter of a cable, it will also generate more heat. And then it becomes very important to know that the backfill material around your cable is conducting enough to remove the heat and make sure that your cable will not be melted or damaged by all this heat that might be generated. Commonly seen around solar and wind farms, for instance, a lot of these are being installed these days, so I'm guessing this is partly why we see a lot of requests related to solar and wind farms where new cable installations are performed. Of course, also geothermal installations becomes very important, like here where we have a ground heating system. Then it becomes very important to make sure that we can transfer enough heat from the bedrock or from the ground, like we have here, into the hoses or tubes that carry the heat transfer fluid. If you cannot harvest the heat from the ground, of course, then the heat pump function will be reduced, and that would be a bad thing, of course. So therefore, you probably want to check the thermal conductivity of the backfill, or it could also be the grout around these installations. We also do see quality control applications. Is the concrete that you work with good enough? Maybe you bought some new product, and you see a number on the package. Is it really that good? Or maybe something with your use of it hampers it, or maybe you can improve it yourself. With TLS 100, such tests are actually very easy to perform. And it can also be used in an R&D application, of course, then where you make new mixtures, you make new materials, you want to make quick tests in your lab. A TLS 100 can really speed up those processes instead of sending the sample away for testing at some expensive institution. Who are these people then, or rather, which is the company buying the machine? And we have everything from small single-person companies and consultants who comes to site, performs measurements from their own company, and then leaves, to large corporations where the entire process is kept in the company. Maybe it's used for R&D, sometimes it's used in the field for construction sites. And we do have quite a lot of technical universities too, where researchers use these machines for different kind of research purposes. And there is actually several peer-reviewed papers featuring our instrument. So it's being put to good use in all kinds of areas. So these are kind of the most common applications. There are many others. We see it even offshore uses and so on, but we can leave it at that for now. And let's have a little bit of a look on the theory that surrounds the transient line source. So we won't dive too deep into the mathematics here, but there are some important points to remember. Now, it's called transient line source since the measurement is transient. So we do use the data during the measurement. We don't wait for a steady state, but we rather look at the evolution of heat during the test time. And for this to work, we must make sure that our sample has a stable temperature. It needs to be at an equilibrium. We cannot have a sample that changes temperature, because this will influence, that means that we will see, that will have an influence on how the needle heats up. We don't want to have any external factor adjusting this. So when the needle is in your sample, we heat it up. So the entire needle is really a heating element, and we measure the temperature increase by a centrally placed thermocouple inside the needle. And this temperature rise is then used to create graphs, or you can use it to create graphs. And you see a picture here in the below. It's a little bit simplified, but basically what we want to do is to plot temperature rise versus the logarithm of time. And this should form a nice straight line, which tells us something about the thermoconductivity. So the simplification here is really that we only look at we remove the initial part of the actual transient, because that will not be straight line, because in the beginning of the transient you will see contact resistance, needle information, and so on, which we want to remove. So that is done, of course, and then you should find the straight line, which is a steady state part of the measurement. And from the straight line here, we will find the thermoconductivity, because it's actually inversely proportional to the slope of the curve. So a steeper slope means that we have a lower thermoconductivity, while a more flat curve gives us higher conductivity. And you do see the equation here. So it might look simple here. Of course, there's more mathematics behind it, but thermoconductivity really comes from the heating power, the power that we give to the needle, and the slope of the curve. So this is the base equation for finding the thermoconductivity, once removing edge effects and so on from the data points. And then you can also calculate the thermal resistance, because it's simply the inverse of the thermoconductivity. So this is the base theory. If you want more theory, you will be able to find that in the ASTM standard. So the machine is made to follow the ASTM D5334 standard very carefully, and it follows this standard thoroughly. And the entire method is very much explained in the standard. So if you want to have all the details, I suggest you can just Google ASTM D5334, and you can buy the standard from ASTM. And the name of the standard is Test Method for Determination of Thermal Conductivity of Soil and Soft Rock by Thermal Needle Probe Procedure. So, as I mentioned now several times, the TLS 100 fully complies with the standard. Each needle comes factory calibrated. So you don't have to worry about the calibration requirements mentioned in the standard. We do this and supply the needle as calibrated in accordance with the standard. So there's no need for the user to do a recalibration. What you do need to do is to check your needle against the verification sample, and if it's out of bound there, you will contact ThermTest, and we can assist with recalibration if need be, or maybe your needle is broken and needs to be replaced. Important to know, I suppose, with the standard is that the standard also governs the size or the dimensions of the needles which are allowed if you want to fully comply with the standard. And our 100 millimeter needle strictly follows the standard. This very shape of needle is described in detail in the standard. However, the 50 millimeter needle, we have developed this to be optimum for testing hard samples and make it convenient for you as a user. But this makes it not fully compliant with the standard because its dimensions are outside of the standard. All the rest related to this sensor, however, follows the standard. So all the calculations, the calibrations, and everything else, and also the construction really follows the standard. But it could be important to know, if you report results, you cannot say that this needle fully complies with the standard. Also mentioned briefly before, we follow another standard which is called IEEE, and that's the standard 442. And it has a few different revisions. The most well known is from 1981, where we follow this for laboratory use. It also has a section for use in the field, but in the IEEE standard field testing, they require really long needles of at least 30 centimeters, and that makes the needles very fragile. So we have, up till now, decided not to go that route because it really generates more problems than it solves to have long needles that tend to be bent and damaged too quickly and easily. So at least the standard is a very nice document to come back to. It's easy to read, so I would actually recommend most users to have a look at it if you want to know a little bit more in depth about the technology. And with that, let's make a little bit of an outlook to what other thermal conductivity measurements you see around. As I mentioned before, TLS 100 is a transient method. There are two types of methods, I should say, for thermal conductivity testing. We do have steady state, which are traditional methods. Famously, ones are heat flow meters, guarded heat flow meters, and most known maybe is the guarded hot plate. Very expensive, very reliable, but for testing soil and samples that the TLS 100 excels at, it's not optimum. It's fantastic for insulation materials, for instance, but for testing soil or a loose sample, it becomes very complicated. The same goes for the other ones above here. Hotbox I mentioned here because there are actually some standards defining backfill material using hotbox method. It's a very expensive method, very complex machine, very large. This can be used in combination, for instance, with the TLS 100 to send as few samples as possible over to testing with a method like the hotbox, which will be very expensive. Typically, testing one sample with a hotbox is more expensive than buying more than one TLS instrument, actually. So more related maybe are other transient methods. They are, of course, not made specifically for testing soil and the samples that we use for the transient line source, but they are versatile in ways that the steady state methods are not. So we have the transient plane source, the laser flash methods, which is great for high temperatures, and transient hot wire methods, which are fantastic for fluids. So they cover different type of materials. All of them come at a higher price tag than the transient line source machine. So if this is your focus, a TLS unit is probably definitely the way to go for your wallet as well as for your ease of use. And talking about ease of use, let's have a look at how to use the machine and how to do it right. Now, of course, I would have to recommend you, if you get this machine, to start with studying the manual and potentially relevant standard if you want the more in-depth understanding of the method. It's not required because the manual will give you a good picture of how to do this right, but the standard might give you some extra insights. So make sure to prepare your samples. Size we have already discussed, so make them big enough, 50 millimeter diameter, and long enough to cover the entire sensor and maybe some. You need to make a hole in your sample. If it's soil, use what we call a poker, which is basically a dummy needle, which you poke into your soil and make a hole, mostly to make sure that while you insert your needle, you don't have any rocks or other problems that you have to use force to push your needle through, because that might damage the needle. So therefore, the poker can really save you if you're in the field and you have a tricky kind of soil to test. Now, if your sample is hard, you will use a drill your hole, and then of course we need to insert the needle. If it's a soil sample, simply put it into the soil. Nothing else you need to do. Just make sure that it seems like the needle is entirely covered by the soil and that the hole doesn't have any big bubbles or so deeper down. If the sample is solid, then we need to use contact paste. You will soon see that in a little video here, but it's important to put contact paste around on the needle for testing solid, simply because we need to have a good contact between the sample and the surrounding material that we want to test. If you don't have this, it will take too long time for us to reach the steady state part of the transient curve that we discussed earlier here. And that means that we will not find a straight line where we expect it to be, and you will get incorrect results, typically too low values. So make sure to use paste for hard samples. So now you're ready to start the instrument. You need to select the correct needle. If you have more than one, if there's only one, it will auto select that and you're ready to go. But make sure to check your battery status. You don't want to run it with almost empty batteries, since that will only interrupt your measurement. Once the machine is on, you will start seeing the temperature of your sample, and you should monitor the temperature before you start your test. Temperature should be stable. And I suggest normally to wait maybe 10-15 minutes, especially if you're doing this in the field, because the needle should probably have a different temperature than the sample itself. And we want the needle to take the temperature of the sample. So sometimes 10 to 15 minutes is not a bad idea to put it to, and you can do this through what we will look at here, automatic testing. But once we are happy with the temperature stability, you're ready to test. Make sure to name your sample. That will make life easier for you later on when you come back and review your data. You can run tests manually. Simply push the start button and go ahead. And it will run a single test and you will get the results on screen immediately. But you can also run multiple tests automatic. Maybe you want to have some statistics. Then you tell the instrument, okay, I want to run 5 tests and I want you to wait 10 minutes between my tests. And then the machine will do this automatically while you maybe prepare the next test location, for instance. After use, make sure that you clean off your sensor. You don't want a lot of paste left on the sensor. It will just dry and make it hard and tricky for you the next test you run. Put it in its protective sleeve. There's a small sleeve along with your sensor that makes sure that you won't bend it or damage it while moving it around. There's also a second picture here where we can use what we call a needle sleeve. Those come, a few of them, along with instruments, so they can be optionally added if this is an application you find interesting. For instance, if you work with concrete, you don't want to drill, you want to use the long needle completely following the ISO standard or the ASTM standard, then we use these sleeves. And when you cast the concrete, you insert the sleeve and you allow the concrete to cure. And then you have a hole made by this sleeve. Just apply the paste to your needle and push it into the sleeve and you can run your test without having to drill or prepare the sample anything more than getting the sleeve in there while the sample was still soft. So quite useful and could really help you to test this more. Hard samples with the longer needle. So how do the results really look? So here we have a picture of the actual screen of the TLS-100. So the results are displayed here, all of them. You will have a sample ID displayed here when you go back and review your data. Test time now, here the date was not set, but you should do that so you can more quickly go back and look at your sample and remember when it actually was tested. And time, of course, so you get the date and time stamp related to your data. Thermal conductivity is displayed here, and thermal resistance here. An important number we see here, which is the correlation. What does this mean then? Well, this is basically how good the measurement data takes shape as a straight line. So we do a straight line fitting in the calculation, and if we see a value close to 1 here, so 0.99, excellent, we are very close to 1, meaning that we have more or less measurement data that shapes a straight line when we plot it as the logarithm of time. If this value falls down, let's say below 0.9, then you don't have a really good fit to a straight line. That means that something is not perfect here. There can be several reasons, but very often it is the temperature not being stable. And what you can do when you see this is you wait a while, redo the test and see if the correlation improves. Then you become quite sure you had a temperature drift going on. And of course, the temperature at the test time is recorded for you to review later. All the results are stored. You don't have to save them manually. It's automatically done. That's at the end of each test, results are saved to the SD card, which sits inside the machine. It can hold thousands of tests, so don't worry, it will not get full. You don't have to run to empty your SD card very often, but it's very easy to transfer your results over to Excel. Simply move the SD card over to a computer through either a card slot or through some kind of USB device to make it easy to transfer the data. and upload it to Excel. It comes in CSV format, so it's really easy to import. And there you can, of course, treat your data. You can generate the tables you want and create reports for your clients, for instance. So pretty easy to work with, I would say. You get everything directly here on the screen. And now that you know how to use the machine, you will also get the chance to see it here. And I will ask Yoli to switch on the video here. There we go. And here you see the poker being used to make a hole for the needle. So it's very straightforward. Needle goes in there, and usually you should twist it maybe there a bit to make sure that you have good contact, and wait before you start the measurement there. And here is the 50mm needle instead. Paste is being applied here to the needle. That's a suitable amount. And while you push it into your sample, in this case concrete, you twist it like this to distribute the paste, and twist it several times, maybe push it up and down a bit like that, and you run your measurement. And here you see fast forward how the measurement proceeds. Sample heats, then cools, and then it will save and calculate your data. So here you see it was a 2-minute test time here. So it is pretty fast, and now it's saving, and there it presents your results. Thermal conductivity and thermal resistance, and the temperature on top there. So that's the procedure, how it looks to work with. Very easy, not too many buttons to worry about, and I think it's very easy and simple to work with. And so what happens with the results then? So this is a lot of data, maybe you will think, but it's quite easy to create a lot of data. And I wanted to show the entire table here, because just to see what you can do with the machine. The sum up comes over here, you can say, but we tested, this is sand samples, or quite coarse, almost gravel, moist and dry. Samples came from a dig site where they were immediately packed in sealed bags to make sure that no moisture was left or escaped the sample during transport. When they arrived at the lab, they were tested. And of course, first we tested the mass and the density to make sure all the samples were comparable in density, because otherwise it's really hard to compare them. Tested in the moist state, you see the average values, it's the lighter lines. Thermal conductivity here, thermal resistance here. After that, all the samples were dried in an oven at something like 100 degrees overnight to make sure all the moisture was evaporated, and we ended up with a dry sand sample. And tested again, which are the darker lines, and you will see the thermal conductivity drops quite a lot. And now, since we could have the mass as both moist and dry, we can calculate the water content in mass percentage. And that's what you see over here. These 2 points are the average of all 5 samples here as moist, something almost 0.5 watt per meter Kelvin. And once all the fluid has left it, we do end up at below 0.3 watt per meter Kelvin. So basically, it's quite important to keep an eye on what happens with your cable or with your soil if you want to have control of thermal properties. So if you would bury a cable here, for instance, this might be your normal case, but in a really long, hot and dry summer, the entire soil might dry up, and you might end up down here. So maybe important for any kind of simulation work to make sure that your cables will actually survive this worst case scenario. And this is something that you could call a simple dryout curve. And you can do this much more thoroughly, but this is something you could actually do in the field to get in situ value, and you can dry your sample with a burner to do this in the field, and you get these curves. Might be good enough. Some applications, on the other hand, you do have to make more advanced dryout curves or more detailed ones. As you see an example here, where we have a moisture content here down on the x-axis and a thermal resistivity. So it's inverse of what we had in the other picture. I will come back to, yes, I can quickly answer this this question here about if it's necessary to insert the entire needle. Yes, it is important and necessary to insert the entire needle. Why? Because we do heat up not the entire needle really, but 1/3 in the middle is where the heat sits, you can say. This is where we measure the temperature also, but the top and bottom part will act as guards to make sure we don't have boundary effects. So it is actually very important that you get the entire needle into your sample. So you cannot have an undersized sample. So minimum sample size, same length as the sample as mentioned before, and 50 millimeter diameter. So back to the dryout curves. As I said here, moisture content here, and this is a little bit different from the last curve where we had mass percentage. This is how saturated the sample is. Fully saturated up here, this is then how much the maximum amount of liquid that you can get into your sample, and fully dry down here. So to create these curves, you start with conditioning your samples. You don't get in situ sample. You have to take your sample to the lab and condition it to reach fully saturated, where you have the maximum amount of liquid you can get into your sample. And here we need to test the density and, of course, the thermoconductivity. After that, it goes into the oven for some preset of time. Maybe you combine this with a scale so you know how much water leaves it. You take it out and you test the thermoconductivity again once the temperature is stabilized. And then you go back to drying until you build up this curve. And once you have all the liquid left the sample, you will have completed the entire dryout curve. And then we, of course, plot the conductivity or resistivity, whichever you prefer, against the water content. So some applications, this becomes important, but it requires much more work, of course, and it needs to be done in a lab. But it's pretty straightforward and not complicated to do this with a TLS 100. You really need a TLS 100, a scale, and an oven, and you can create curves like these. Now that concludes the soil testing example, and we will have a fairly quick look at testing concrete because it's really straightforward. Now here's an example of testing concrete. In this example, we have two pieces here of sample. Both are in the base is an environmentally friendly or green concrete, if you want, made of 80 to 90%, something like that, recycled material. So it's probably old concrete and so on being mixed in here to make the concrete more affordable and, of course, more friendly for our planet. And you see the results here. The first sample to the left here is the based concrete. Fairly high thermoconductivity for this type of concrete. But the application it was supposed to be used for here was actually floor heating for bathrooms and so on, where you want these nice warm floors, where you want the heat nicely and evenly distributed, and you don't want the heat to be going backwards into your insulation layers. So the second sample, 10% of graphite powder was mixed into the concrete and cast, and then thermoconductivity was tested of this sample, and you see the thermoconductivity increases with 1 here. So it's quite a big increase, more than 50% increase by adding graphite powder to concrete. And this is a very nice and I would say very straightforward R&D application. And this is done with a TLS in, well, if you cast your sample, this testing is done in just an hour or something like that to get this kind of data. And the plus minus here is 3 measurements on each sample. So the standard deviation from 3 measurements is pretty low. So this is much better than 1%, I think, and or at least around 1%. So pretty good, given that. So, and of course, here's the thermal resistivity. So that is the way to test concrete. And after that, we will actually move over to a little bit of a summary of this presentation, just to have a look at what we actually talked about. So the TLS 100 is a very popular machine for in situ and also for laboratory testing. It follows the ASTM standard D5334, which is designed according to, and it also complies with a lot of parts, at least the big parts of the IEEE 442. It's an affordable transient instrument, very easy to use, and it can test a fairly wide range of samples. Soil, rock, concrete, asphalt, and polymers being the most common one, but we have also seen testing of, for instance, wood and other types of samples. So it has quite a lot of potential in a small frame. And by that, I would like to say thank you for listening to the presentation part. I will hand over to Jolie now for a quick little reminder, and then we will go and have a look at the questions. Thank you, everyone.
Thank you, Daniel. So before I go ahead and read questions, I just wanted to remind you guys again of the upcoming webinars for August and September. And now it's the Q&A period. So any questions that we aren't able to answer during this period will be sent in an email on Thursday, July 9th, along with a recording of the webinar. So I will go ahead and read the first question.
Yes, just hang on a second, so I have time to quickly read some questions here. Okay, first we have a request here for an application in a case study in agriculture. I think we might have that. We do have several applications up on our homepage on thermtest.com where you can quickly have a look on that. And I will we make a note on that, and Jolie will send you something if we have something special there for you. We can have a look at this one here. So if you have a hard sample, as you see here, asphalt, for instance, which might be sticky because of temperature. Now, I would say during the test time, now the sensor will heat up quite moderately. So it's not a big temperature increase. And of course, if you're in a very hot day and the concrete might be very, very close to becoming melting anyway, yes, then this might be an issue, because then we are starting to look at the phase change. I would suggest testing a sample like this not too close to the temperature of softening. But if you would do this, let's say in a 20-degree outside temperature or something like that, then your sample will not become soft or sticky due to the needle. If you test it already in a temperature where it's sticky all the time, then I don't think you see an issue either. If you're worried about this, you can set the instrument to use a low power to limit the temperature rise. Might give you a little bit more noise, but it might be a nice way to avoid having any phase changes occurring or interrupting your results like that. And yes, as Dale points out here, yes, you can cover the needle with paste. That might help also. And normally you should probably use that anyway, because the asphalt will count as a hard sample. So to make sure that you have nice and good contact, use paste anyway, and probably your needle won't stick thanks to that also. Okay, here is a more general question on thermal conductivity. So thermal conductivity, very quick answer to this might be to say that the thermal conductivity tells us how much heat can be moved through a material. Thermal resistance is really it's the opposite, right? So this is gives you a value of how hard it is for the heat to travel through the material. So an insulation material per definition has a low thermal conductivity, but a high thermal resistivity. So depending on your field of work, you prefer to work with thermal conductivity or you prefer to work with thermal resistivity. But for the example of underground cables, for instance, we want to probably have a pretty high thermal conductivity to make sure that we can get rid of heat. So this is maybe the practical application. With a high conductivity, we can get rid of or move much heat through the material that we're looking at. while if you have a low thermal conductivity, it's hard to move the heat through it. Perfect if you want to insulate your house. You don't want the heat to escape your house, you want the low thermal conductivity. So hopefully that answers it. So here's a quick question. So a question about watts per meter Kelvin to watts per meter Celsius. You don't have to convert, it's the same thing, because the size, 1 Kelvin is as big as 1 Kelvin is the same as 1 Celsius, of course. Now, we don't have to worry about where we have 0 because it's just a unit. So you will say watt per meter Kelvin at a certain temperature. You can just as well say watt per meter and Celsius at a given temperature, but that is quite uncommon to do that, I would say. So this is I found this question here. The difference between different methods. So when we say accuracy, 5% or better, this is really when you compare different methods. So a TLS 100 should compare with another type of TLS instrument or to a completely different method if the samples are isotropic and otherwise comparable, normally within 5%. This is what the calibration is supposed to do. So if the sample follows or falls into the range where you should use these instruments, they should be within 5% from each other. That's what we mean with accuracy. So I hope that answers that part of the question. And let's see if we can do maybe one more. I will allow first Yoli to answer this. A copy of the presentation, I think we will publish the presentations, right?
In an email. So it'll just be one video, but you can share that with your colleagues if you please.
Yep, so everyone attending will get a copy and then you should be able to share that if I understand that correctly. And let's see, we can do at least, I will do 2 more here. So starting with this one. So when might you damage the needle? Well, there might be a few occasions, I suppose. One is the most common I see is when you test soil, you don't use the poker. There are stones in the soil and you might be in a hurry. You just push in the needle and that was a pointy or sharp stone and that can bend or just damage your needle quite a lot. And that might actually render it completely useless. So be careful, use the poker to not damage it like that. Also, don't use the needles underwater. There might be, because they might leak in water and you can short circuit it. So no underwater testing and be careful when pushing needles into unknown samples. And then we have an important question here, I think, about lifetime of batteries. So batteries that we use, that we recommend, are lithium batteries. Normally we say that you should use Energizer Ultimate Lithium, I think they're called. If you use these high quality lithium batteries, you will have normally hundreds of tests from one set of batteries. It depends, of course, if you go to really long measurement times, it might be limited, but that is what we expect. If you, on the other hand, go to the local supermarket and buy some cheap alkaline batteries, you might only get a handful of tests because these don't keep the voltage on a nice flat level like the lithium batteries, and then the machine will find, oh, we have a drop in voltage and it will interrupt the measurements. So if you use the good batteries, you will have many tests and you should see no issues from that really. But if you use cheap batteries, it might be something you can do in a worst case scenario. You're out in the field, you forgot to bring your batteries, but I really do recommend do get these more expensive batteries, it will pay off in the long run. And just browse through if we have some more quick question here that we can take before we round this off. There is questions about if we can name people who use this. We can discuss that, but that would be in person because often there is a little bit hard to say anything about exactly who uses it. But we do have several hundreds of these machines in the field, so there are quite a lot of users for sure.
So I think that concludes our Q&A period. Is
Yep.
that good? All right. So all of the remaining questions that we have not addressed yet will be answered on Thursday in the email. I'd like to thank everyone for joining us today, and we will see you next time.